In this video, we are going to see the JEE main previous year questions from the topic D block elements. Let us see the key concepts first. You have to know the position of D block elements. The D block contains the elements of the groups 3 to 12. These elements are also called as transition elements because their properties are in between the S and P block elements. So, they are considered transitional between the S and P block elements. This D block contains 4 rows and each row is considered as a series. The first row is called as 3D series because in this row the 3D orbitals are partially filled. The second row is called as 4D series. The third row is called as 5D series. Fourth row is called as 6D series. You have to remember all the elements present in the D block. The best way to remember the elements present in the periodic table is you have to go group wise. You have to start from scandium, yttrium, lanthanum, actinium. Likewise, you have to study. Concept is electronic configuration. The general outer electronic configuration of D block elements are n-1d 1 to 10, ns 1 to 2. The d orbital has the electron range between 1 to 10 and s orbital has the electron range 1 to 2. So, let us take the example of scandium, which is having the atomic number 21, and see its electronic configuration. So, you have to start from the 1s orbital, 1s2, 2s2, 2p6, 3s2, 3p6. So, up to this 18 electrons are filled. This can be represented as the core orgon configuration. So, after 3p orbital, you are having 3d orbital and 4s orbital. Now, we are going to compare the energy of 3d orbital and 4s orbital using the n plus L value. So, you are going to see the n plus L value of 3d orbital. The n value of this orbital is 3 and the L value of d orbital is 2. So, 3 plus 2 equal to 5. And for 4s orbital, the n value is 4 and the L value of s orbital is 0. So, 4 plus 0 equal to 4. So, what is the n plus L rule? Higher the n plus L value, higher is the energy of the orbital. So, you can see that the n plus L value of 3d orbital is more than the 4s orbital. So, the energy of 3d orbital is greater than the energy of 4s orbital. So, according to Aufbau principle, electron first enters the 4s orbital, then only it moves to the 3d orbital. So, after filling the 3p orbital, the next electron is going to enter the 4s orbital, then only it will go to the 3d orbital. So, up to this we are having orgon configuration. Orgon configuration represents the 18 electrons. The next electron will enter the 4s orbital. 4s orbital can accommodate 2 electrons. So, already 18 electrons are there, then 2 electrons are filled in 4s orbital, then remaining you are having only 1 electron. So, the remaining 1 electron will enter the 3d orbital. So, you can write the general electronic configuration as core orgon configuration 3d1 4s2. So, this is the general electronic configuration of scandium. Now, moving to the next element, titanium, core orgon configuration. Then after that you are having 3d orbital and 4s orbital. So, the next 2 electrons enters the 4s orbital, then the remaining 2 electron enters the 3d orbital. Then going to the next element, vanadium, core orgon configuration 3d3 4s2. So, this is how the electronic configuration is written for the D block elements. Here, if you compare the electronic configuration of these 3 elements, the difference lies in the number of d electrons, and this d orbital is present as the penultimate energy level. The last one is ultimate energy level and the last before shell is penultimate energy level. So, the penultimate energy level is receiving the electrons in the D block elements. Next concept is exceptional electronic configuration. There are some exceptions in the general electronic configuration of D block elements, and these exceptions are based on the fact that half filled and completely filled orbitals are more stable. So, there are some exceptions. We will see that. So, we will take the 3D series and we will first see the electronic configuration of all the elements. So, for scandium we already saw 3d1 4s2, titanium 3d2 4s2, vanadium 3d3 4s2, chromium 3d4 4s2, manganese 3d5 4s2, iron 3d6 4s2, cobalt 3d7 4s2, nickel 3d8 4s2, copper 3d9 4s2, and then you are having zinc 3d10 4s2. So, these are the expected electronic configuration of this 3D series, but there are 2 exceptions in the electronic configuration, and the 2 elements are chromium and copper. So, we will see the exceptional electronic configuration of chromium, which is having the atomic number 24. So, what is the expected configuration? core argon configuration and 3d4 4s2 is the expected configuration, but the observed configuration is one electron from the 4s orbital is promoted to the 3d orbital. So, the observed configuration is core argon configuration 3d5 4s1. Why the one electron from 4s orbital is promoted to 3d orbital is this 3d5 configuration is half filled configuration. D orbital can accommodate a total number of 10 electrons. So, this 3d5 is half of that configuration. So, it is half filled configuration which is more stable because of symmetrical distribution of electrons and exchange energy. So, because of this concept, the half filled configuration is more stable. So, the one electron from the 4s orbital is promoted to the 3d orbital. Then going to copper, which is having the atomic number 29, the expected configuration is argon configuration 3d9 4s2. Here also one electron from the 4s orbital is promoted to the 3d orbital. So, the actual configuration is argon configuration 3d10 4s1. So, here the reason is fully filled d orbital is more stable due to symmetrical distribution of electron and exchange energy. So, in 3d series only two elements show the exception in their electronic configuration. The same exceptional electronic configuration is also observed in the other series of the d block elements. So, let us compare that with the 3d series. In 3d series, as we already saw, only chromium and copper is having the exceptional electronic configuration. So, this is the 3d series. Now, we will move to the 4d series. In 4d series, 7 elements are showing the exceptional electronic configuration. The elements which are given in white show the exceptional electronic configuration. So, starting from niobium up to rhodium, the s orbital is having only one electron. So, first we will compare that with the 3d series. Vanadium is having the configuration 3d3 4s2. So, niobium, which is coming after vanadium in that group, should have the configuration 4d3 5s2, but due to the increased nuclear charge, when we go down the group, one electron from the 5s orbital is promoted to the 4d orbital. So, the actual observed configuration in case of niobium is krypton configuration, core krypton configuration 4d4 5s1. So, this is the observed exceptional configuration in case of niobium. Then going to molybdenum, which is coming after chromium. So, we can tell the same reason. Molybdenum should have the configuration 4d4 5s2, but it is having 4d5 5s1 configuration. So, here the half filled configuration is more stable, but we can also say the same explanation that when we go down the group, the nuclear charge increases and one electron from the 5s orbital is attracted to the inner orbital. So, that reason is the explanation for the other elements. Technetium, which is coming after manganese, also should have the configuration as 4d5 5s2. Here also one electron is attracted to the inner shell. So, 4d6 5s1. Then going to ruthenium 4d7 5s1. Then for rhodium same 4d8 5s1. So, for all these 5 elements, the 5s orbital, or you can say the s orbital, is having only one electron. So, all these elements show exceptional electronic configuration. Then going to palladium, which is a very special element and it is having a special exceptional electronic configuration. So, palladium, which is coming after nickel, palladium should have the electronic configuration as core krypton configuration 4d8 5s2. This is the expected configuration, but here both the electrons from the 5s orbital is promoted to the 4d orbital. So, the actual configuration is core krypton configuration 4d10 5s0. So, in this case, the fully filled d orbital is more stable. So, for that reason, both the electrons from the 5s orbital is promoted to the 4d orbital, and as we go across the series, the size of the elements also decreases. So, the increased nuclear charge allows both the electron from the 5s orbital to be promoted to the 4d orbital in case of this palladium. Palladium is the only element which is having 0 electrons in the s orbital. All the other elements will have either 1 or 2 electrons, but palladium is the only element which is having 0 electrons in the s orbital in case of this d block elements. Then going to silver, which is coming after copper, we can tell the same reason. It is having the configuration 4d10 5s1. So, the fully filled orbital is more stable. So, these are the exceptions in case of 4d series. So far we have seen the exceptional electronic configuration of 3d series and 4d series. Now we will see the exceptional configuration of 5d series. In 5d series only 2 elements exhibit the exceptional configuration. The 2 elements are platinum and gold. You can think that why tungsten does not exhibit exceptional configuration, because previous to tungsten, molybdenum and chromium both exhibit half filled d orbital configuration, which is more stable, but tungsten does not exhibit that half filled configuration. Configuration of tungsten is 4f14 5d4 6s2. Why the one electron from 6s orbital is not promoted to 5d orbital? Because here due to relativistic effect, that is in heavier atoms As we go down the group, the elements becomes more heavy. So in heavier elements, there is some relativistic effects, and that relativistic effect makes the s orbital more stable and the d orbital is destabilized when compared to the s orbital. So the energy required to promote the 1 electron from the 6s orbital to the 5d orbital is more. So that energy is not compensated by the half-filled stability. So after the promotion of 1 electron from the 6s orbital to the 5d orbital, stability is attained, but even though stability is attained, still the energy required is more. So there is no promotion of the 6s orbital electron from 6s orbital to the 5d orbital. So if we see platinum, the expected configuration is 4f14, 5d8, 6s2. This is the expected configuration. Here 1 electron from the 6s orbital is promoted to the 5d orbital. But when you see palladium, it is having the configuration 4d10, 5s0. Here both the 5s electrons are promoted to the 4d orbital, but in case of platinum, only 1 electron from the 6s orbital is promoted to the 5d orbital. So the actual configuration is 4f14, 5d9, 6s1. So here also the same reason, the energy required to promote both the electrons into the 5d orbital is more, and it is due to the relativistic effect. So in case of platinum, only 1 electron from the 6s orbital is promoted to the 5d orbital. So the electronic configuration of palladium is also special and platinum is also special, or you can say it is different from the other configurations. And then we are having gold, which is in the group as copper, silver and gold. They are having the same outer electronic configuration. So they are having fully filled d orbital. So the configuration of gold is 4f14, 5d10, 6s1. So the fully filled configuration gives extra stability. So the elements which are given in white, these elements have exceptional configuration. You have to memorize that. The next point is their physical properties. They are solid metals with high tensile strength, ductility, malleability and thermal conductivity. That is, they are good conductors of heat and electricity. So the transition elements except zinc, cadmium and mercury. So the group 12 elements, zinc, cadmium, mercury, have the general configuration in which the d orbitals are fully filled and the s orbital is also fully filled. For example, let us take zinc. Zinc is having the configuration 3d10, 4s2. Even in the +2 oxidation state, zinc is having 3d10 configuration, that is the fully filled d orbital. So the three elements in group 12 are not considered as transition elements because only the partially filled d orbital, only the element which is having the partially filled d orbital should be considered as transition element. So the group 12 elements are not considered as transition elements. They are not transition elements. So if you see the properties of the transition elements, the group 12 elements will be an exception in that property. So the other transition elements are hard except this zinc, cadmium and mercury, which belongs to the group 12, and this mercury is a special element which is a liquid metal. So all the other elements are solid metals, but this mercury is a liquid metal. So they are having high melting and boiling points. This high melting and boiling point suggests that they are having strong metal-metal bonds. Strong metallic bonds are there, and as the number of unpaired electrons increases, the metallic bonds also, the metallic interaction also increases. So this suggests that they have high enthalpies of atomization. Enthalpy of atomization means the conversion of this solid metal into gaseous atoms or gaseous ions, or you can say gaseous individuals, is called as the enthalpy of atomization. So this enthalpy of atomization for the d block elements are more. So if you consider the 3d series, in 3d series the element having the highest enthalpy of atomization is vanadium, which is having the configuration 3d3, 4s2. So there is no repulsion, electron-electron repulsion, and the maximum number of unpaired electrons is 3. So vanadium is having the highest enthalpy of atomization. You can consider chromium and manganese, which is having 3d5 configuration, but that configuration is already more stable. So the isolated form of chromium and manganese is already stable, but for vanadium, the isolated form of vanadium is not stable, only the metallic form is stable. So for the conversion of the solid metal into the isolated gaseous atom, more energy is required. So the highest enthalpy of atomization in the 3d series is for the element vanadium. The next concept is the variation of atomic and ionic sizes. So as we move across the series, the nuclear charge increases by 1 unit and the incoming electron is added to the d orbital. So we already know that d orbital exhibit poor shielding effect. So due to the poor shielding effect, the increased nuclear charge attracts the outermost electron more towards itself. So as a result, the size decreases. When we go from scandium to zinc, across the series, the size has to decrease, and the concept is due to the increased nuclear charge and the incoming electron is added to the n-1 d orbital, and this d orbital is having poor shielding effect. As a result, attraction is more and the size has to decrease. But as we can see here the atomic and ionic size or ionic size is given in picometer. So we can see the trend from scandium to titanium there is a decrease, and this decrease continues up to chromium. So for chromium you are having the least atomic size in this 3D series. So we can tell that in this 3D series chromium is having the least atomic size. So when we see the next element manganese, there is a slight increase in the atomic radius of this manganese when compared to chromium. So what is the reason for that? The electronic configuration of chromium is 3d5 4s1. The electronic configuration of manganese is 3d5 4s2. The 2 electrons present in s orbital is having electron-electron repulsion, and we also know that the screening effect or the shielding effect of s orbital is more than the d orbital. So as the outermost electron is more shielded from the nuclear charge, there is a slight increase in the atomic radius when compared to chromium. Then as we go to the right side of the series, the atomic radius is almost the same for these elements. This is because here the d electrons are paired and there is a slight increase in the shielding effect, and therefore the nuclear charge is not sufficient to attract the outermost electron towards itself, and the size is not reduced in this case, and it is somewhat similar because the nuclear charge is not that much sufficient to attract the outermost electrons more inwards. So the size remains the same. And if you go to copper and zinc, there is a slight increase in the atomic radius. From nickel to copper, there is an increase in atomic radius, and from copper to zinc also there is an increase in atomic radius. This is because copper and zinc do not have any unpaired electron. They have fully filled d orbital. This fully filled d orbital is having more shielding effect, and therefore the nuclear charge is not sufficient to attract the outermost electron, and thus the size increases. Next concept is lanthanoid contraction. As we go down the group from the 3D series to the 4D series, there is an increase in the atomic size. This is actually the usual explanation. When we go down the group, the number of shells increases. As the number of shells increases, the distance between the nucleus and the outermost electron also increases, and therefore the size increases. So this is the trend observed when we go from the 3D series to the 4D series. But when we go from the 4D series to the 5D series, the atomic size remains the same. So this trend in which the atomic size remains almost the same for the 4D elements and the 5D elements is called as lanthanoid contraction. Why? Because in the 5D series, after the element lanthanum, you are having 14 F block elements which are called as lanthanoids. So after these lanthanoid series are completed, then only you are having the next element hafnium. So if you can see that there is a difference in the atomic number. The lanthanum is having the atomic number 57 and hafnium is having 72. So in between you are having 14 elements which are the F block elements. So we can say that when this element hafnium is starting, there is already fully filled F orbital which is present here. 4F orbital is present in the electronic configuration of the element hafnium. So throughout this series there is fully filled 4F orbital present, and we know that the shielding effect of F orbital is even very poor than the d orbital. So we can write that the F orbital exhibits very poor shielding effect, and because of this poor shielding effect, the nuclear charge also is attracting the outermost electron more towards itself, more inwards, and as a result the atomic size decreases. But we saw that down the group the atomic size should increase. So both these effect compensates each other, and there is no increase in atomic radius, also there is no decrease in atomic radius, and the atomic radius remains the same for the 4D element and the 5D element. So this effect is called as lanthanoid contraction, in which the 5D series is having fully filled 4F orbital. So there is a poor shielding effect and the atomic size is the same. Concept is oxidation states. The d block elements exhibit a wide variety of oxidation states. So we can see the oxidation states of the 3D series. Scandium exhibits only one oxidation state, and that is +3. The electronic configuration of scandium is 3d1 4s2. So after the loss of all the 3 electrons, scandium acquires noble gas configuration, that is argon configuration. So in scandium the only oxidation state that is stable is +3 oxidation state. Similarly, if you go to the extreme other end of the 3D series, that is zinc. Zinc also exhibits only one oxidation state, that is +2 oxidation state. Zinc is having the electronic configuration 3d10 4s2. After the loss of 2 electrons, it acquires fully filled d orbital configuration 3d10. So these are the 2 elements which exhibits only one oxidation state, and questions can be asked, which is the element which exhibits only +3 oxidation state? So that is scandium. Then if you see the elements which are present in middle, all these elements exhibit +2 oxidation state. So in all these elements +2 oxidation state is common, and copper is the only element in which +1 oxidation state is also possible. So throughout this 3D series, copper is the only element which can exist in +1 oxidation state. Then the element which shows a more number of oxidation state exists in the middle of the series. So that element is manganese. Manganese is the only element which shows oxidation states from +2 to +7. So it shows totally 6 oxidation states, and the element which shows more number of oxidation state always exists in the middle of the series. As we go to the heavier elements, that is 4D series and 5D series, these elements show higher oxidation states. That is, the elements present in 4D and 5D series have stable compounds present in this higher oxidation state. The reason is, in 4D and 5D elements, the d orbitals are already more diffused and they are spreaded out in space. So it is easier to take the electron from this d orbital when compared to the 3D orbital. So these elements which are present in the 4D and 5D series have stable compounds in their higher oxidation state when compared to the 3D series. For example, in group 6 elements, that is chromium, molybdenum, tungsten. So this chromium, as you can see, it exhibits +6 oxidation state also, but that +6 oxidation state of chromium is not stable when you compare that with the molybdenum and tungsten. Molybdenum and tungsten have stable compounds in +6 oxidation state. As I already told, their d orbitals are more diffused and it is easier to take the d electron from that orbital when you compare to 3D series. The concept is the stability of higher oxidation states. The higher oxidation states are usually stabilized by fluorine and oxygen atom. The reason is, both these elements are more electronegative, so they attract the electron cloud of the metal atom and they form a stable bond between the metal. And you can also tell that fluorine atom has the high lattice enthalpy. When a bond is formed between the fluorine atom and the metal, it has high lattice enthalpy, so the bond is more stable and the higher oxidation states are stabilized. Oxygen atom forms multiple bonds with the metal and it is going to stabilize the metal atom. So the small size and the more electronegative nature of fluorine and oxygen is favorable for the stabilization of the higher oxidation states of the metal. Concept is the trends in the M2 plus bar M standard electrode potential. So this is the conversion of the solid metal M to the metal in +2 oxidation state. So for this, some energy is required and that we are going to see in terms of the standard electrode potential. So the standard electrode potential of the 3D series are given. So as you can see the values of the electrode potential, copper is the only element which is having positive standard electrode potential. So from this we can understand that copper is not easily oxidized to Cu2 plus. That is, copper by the loss of 2 electrons will become Cu2 plus. So for this step, more ionization energy is required. For the removal of 2 electrons from the copper and for the formation of Cu2 plus, the ionization energy required is more and it is not compensated by the hydration energy. That is, Cu2 plus, when it is present in the aqueous solution, it is hydrated by the water molecules. So there is some release of the hydration energy, but that hydration energy does not compensate the ionization energy that is required for the removal of the 2 electrons. So copper is not easily oxidized, but rather than that, copper is easily reduced. That is, copper present in +2 oxidation state easily accepts 2 electron and gets converted to its metallic form. Readily it is converted to its metallic form. So copper is the only element which is having positive electrode potential, and from this we can tell that copper does not liberate H2 gas from dilute acids. We know that hydrogen is having the standard electrode potential value of 0 volt and copper is having 0.34 volt. So copper is easily reduced, but it is not easily oxidized. And you also know that in reactivity series also copper lies below hydrogen. So copper does not liberate H2 from the dilute acids. This is the trends in the M3 plus bar M2 plus standard electrode potential. That is the conversion of M2 plus ion to M3 plus ion by the loss of 1 electron. So if the standard electrode potential value is more negative, then it is easy to convert the +2 oxidation state into the +3 oxidation state. So if you see scandium, it is having a high negative value, or you can say very low value. So it suggests that scandium is stable in +3 oxidation state. And why? Because after the loss of all the 3 electrons, that is 3d1 4s2, after the loss of all the 3 electrons, it acquires noble gas configuration, organ configuration. So it is easy for the conversion of the +2 oxidation state to the +3 oxidation state. Then similarly for iron also, the value is low. In the trend the value is low, so it suggests that iron is stable in the +3 oxidation state, because in that oxidation state it will be having 3d5 configuration, which is the half filled configuration. If you compare the values of manganese and zinc, for both manganese and zinc the value is high. So, the high value of the standard electrode potential suggests that these two ions are stable in their +2 oxidation state and they cannot be easily oxidized. So, in Mn2 plus the configuration is 3d5 and Zn2 plus the configuration is 3d10 and more energy is required to take the another electron from this +2 oxidation state. So, it is already stable. So, they have the high electrode potential. If you see the value of vanadium, it is negative, but it is less negative electrode potential value, because this vanadium also is stable in V2 plus state, because in this state it will be having 3d3 configuration, which is the half filled T2G configuration, T2G3 configuration, which is also more stable.